We can represent ROM information in a truth table. So programming a ROM is as easy as setting up a truth table and having the programmer program it electronically blowing fuses. So if we have a 2K by N ROM, our truth table would need 2K rows and K plus N columns. K columns to represent the inputs and N columns to represent the outputs, and of course the 2K rows to represent each of the different combinations of our address K. So here we have an example of if we had a 32 by 8 ROM or a 2 to the 5 K or 2 to the 5 by 8 ROM. Here our truth table representation, we have our 5 inputs and our 8 outputs. So here's our truth table representation of that, and here could be our what we'd program. So we'd program this for example, A7 I thought as a function of the inputs 4 through 0 is the sum of just the sum of the minterms. So in this case it looks like A7 is a we have a 1 here, so we have a 1 at 0, we have a 1 at 2, we have a 1 at 3, and then we have a 1 at 29, and in here is whatever it is. So we could represent it as a sum of minterms, and our ROM programmer just needs to receive this truth table. So we have the 32 rows and 5 plus 8 columns. So this is shortened. This in here, we're just not showing what those different combinations are. So it could be a pretty big truth table, but it's still just a truth table, just the same. So we can simplify our combinational logic just using our sum of minterms. We don't need to use a Karnoff map to simplify it in any other way. So that's what makes programming with a ROM very easy to do. So again, our 2K by N ROM, essentially a single device including both the decoder and the OR gates to generate the desired output of any of these sum of minterms, right? So inside our decoder is all the AND gates, and here we have the OR gates, so it just gives us our AND or sum of minterms. So again, our K input lines is our K input variables, input address lines, and our K times 2 to the K generates those 2 to the K minterms of the K inputs. And then depending, we can vary how many outputs we need, so those N outputs or the OR gates give us the sum of minterms of our Boolean functions. So a 2K by N ROM, essentially a single device including both the decoder and the OR gates to generate any of the desired combinational circuit as a sum of minterms. So each of the N outputs is the sum of our 2 to the K minterms. So implementing a combinational circuit by ROM, we only need that ROM truth table. The truth table instructs the connecting of the cross points in terms of blowing the fuse or not. We don't need any internal logic diagram, just this truth table, or we can write it as sum of minterms. So our procedure is just determine the size of the ROM, obtain the programming truth table, and then use the device to blow the fuse pattern. So if we look at an example, if we wanted to implement the function f of x is equal to x squared, that we need to know, well, how many bits can x be? So if x is a 3-bit number, we want to generate an output that's equal to the square of that input number. So in doing so, we need to then, if we have a 3-bit number, those are our 3 inputs, and our output, so we can get a 3-bit number can be anywhere between 0 and 7. The square of 0 is just 0. The square of 7 is 49. So how can we represent each of those outputs? 49, to represent 49, we need 6 bits at our output. So again, our process, determine the number of inputs and the number of outputs to generate a truth table. Look for a useful pattern in the truth table. Maybe we don't need to represent each of those outputs in the ROM. Maybe they're going to be 0 all the time, for example. So then we look, can we implement it with a ROM? If we can implement it with a ROM, we draw a block diagram and the ROM truth table. So if we look here, our 3 inputs, all combinations of those 3 inputs, 0 to 7, that's the input, that's a block diagram to our function. And our output, how many outputs do we need? So we're going to need, 7 squared, 49, we're going to need 6 outputs. So those 6 outputs we'll say, B 0 to 5, we're using those for the outputs, and then we can, code this our decimal equivalent to check to make sure that we correctly designed our outputs, converted from decimal to binary properly. But if we look here, if we're going to implement this with a ROM, we could do this with a 3 by, what's this, 3 by 6 ROM, 3 inputs, 6 outputs. But do we need to? If we look here at B0, B0 looks like it's exactly the same as A0. So we don't necessarily need to put this into the ROM. If we look at B1, B1 is 0 all the time. So we don't necessarily need to put that into the ROM. So that's step. So we need 3 inputs and 6 outputs to our function. But since B0 is A0 and B1 is equal to 0, we don't need them in our ROM. So we can, instead of using an 8 by 6 ROM, we can use an 8 by 4 ROM. And here's our ROM truth table. And then we can just tie B1 to 0 or ground, and B0 we can just tie that to the input A0. And that gives us what's inside our function block to implement f of x is equal to x squared. So that's one example of programming a ROM with a truth table. Excuse me, solving a problem, right, and using a ROM to help implement that. So just a portion of that we use the truth table to implement with the ROM. Let's look at another example. So here we want to use a ROM to implement these 3 functions. So we have 3 outputs, x, y, and z, and we have 2 inputs, A and B. So we can put that into a truth table where we have our inputs, A and B, and then we have our outputs, x, y, and z. So all combinations of our inputs, 0, 0, 0, 1, 1, 0, 1, 1, and then x is just A or B. So we have 0, 1, 1, 1. Y is the exclusive OR, 0, 1, 1, 0. And Z is A, B not. So only if A is 1 and B is a 0, the rest of them are equal to 0. So there's our truth table. We would need then a 2 by 3 ROM. So we'd need a 2 by 4 decoder with 3 outputs. So if we look at our ROM, how can we then program that ROM? So this will do the programming for us, but if we were looking at the ROM schematic, what will that look like? So we got to be a little bit careful. We've got 2 address inputs. So at our address inputs, we have, let's say, we have S0 and S1 at our inputs. At S0, we have to have B at S1. Oops, what happened to that? Let's try it again. Pen stopper. We'll try it here. Maybe it didn't like, here we're getting some funk going on. All right, let's try this. Let's just switch over to here. So here, S1 we have A, most significant. S0 we have B. Then when we're doing this programming, we got to be careful. This output of this decoder has 3 at the top and 0 at the bottom. So again, we put an X where our fuse is intact. That's where we're going to have a 1, and we put no X where there's a 0, and we can program this with this ROM this way. So we get our 2 inputs, 3 outputs. We need a 2 by 3 ROM. So let's look at just one more example here. If we want to make a truth table to represent this ROM. So the verse is, if we can read the truth table, let's see if the pen will work now. We have at our input now, our inputs are X and Y, and our outputs are A, B, C. So we still have our 4 variations of the inputs, 0, 0, 0, 1, 1, 0, 1, 1, and then being careful because we have the 0 at the bottom down here. So again, where the fuse for A, where the fuse is intact, we have an X. Where it's blown, and if it's intact, we get a 1. So we're going to have a 0, 0, 1, 1, and we'll do that in red. 0, 0, 1, 1, and here we'll have a 1, 0, 0, 1, and here we'll have a 0, 1, 0, 0, 0, 1, 0, 0. So now we can say A is just equal to X, and again that's if X, let's do our S1 and S0 the way these are going in, right? A is just equal to X, B is equal to X exclusive or Y prime, it's the equivalence function, and C is just equal to, what is C equal to? C is equal to X naught Y. So we can go back and do our analysis of the ROM schematic. All right, so that's it for this video.